Today we'll be talking about oscillations, so let's jump right in. So the purpose of this experiment is going to be to generate a computational model that can predict the motion of an oscillating spring mass system. And the fundamental physical principles that we'll be using is the energy principle, which states that the energy of the system equals the work done on the system by the surroundings. And the different energies that we'll be using are going to be the kinetic energy, spring potential energy, and gravitational potential energy, which we'll see later on. And we'll be using Newton's second law for the update of the velocity and position. And for results, we'll see that our computational model had some errors, and we're actually pretty close. So for our methodology, first we're going to be taking a video and we'll be analyzing it in Tracker, and using that data we'll be generating a code to make the computational model, and then we'll be comparing the two. So for our Tracker video, the axes are in pink, and the positive x-axis towards the right, the negative x-axis towards the left, the positive y is up, negative y is down. Calibration stick in this case is 0.7 meters, and that's going to tell our code the scale of our experiment. And the red dots represent the positions of the mass at different time intervals. So for our code, we start by defining our variables. The mass of our ball is going to be 0.402 kilograms, and the initial conditions of our system is going to be the position of the ball is going to be the first value that we find in Tracker, as you can see here, and the initial velocity of the ball is going to be 0 because it's going to start from rest. And our G, the K of the spring, and the L naught of the spring are going to be given. And after that, we have to find each energy with the values that we are given for the initial state. So our kinetic energy equation is based off of the kinetic energy equals 1/2 times mass times the velocity of the object squared. Our potential gravitational energy equals mass times g times the y position, and the spring potential energy equals 1/2 times k of the spring times s, which is how much the spring compressed or stretched, squared, and the total energy is going to be all three of those energies added together. After that, after we've defined our initial energies, we have to tell the machine that those initial energies are the ones that it's going to use for the initial values. And after that, we go ahead and find the F net so that we can use Newton's second law to be able to find the update of the velocity and the update of the position. And after that, we have to recalculate our energies because they're going to change based on how much the velocity of the ball and the position of the ball changed. So it's basically a copy paste of what we have up. For our results, we can especially see on the right graph that the red line represents the experimental data, and while the blue one represents a computational model. They look similar, but there are some errors, and that's mostly due because of human error, because these points were not accurately found. They don't not accurately represents the center of mass. And there's also the fact that not all external forces are accounted for, such as air resistance. So now what does it mean? So is the energy principle satisfying? The answer is yes, because since in our computational model there's no external force acting on the system, we would expect our change in energy to be 0, and that's exactly what we see here. So that's good. And now we can find the period of oscillations of our tracker data in the x and y direction. as we can see here. In the x direction, it's about 1.1 seconds. In a right direction, it's about 0.7 seconds. And it differs a bit, probably because of the external forces acting on the system. So in conclusion, the computational model came close but still differed to the real model due to human error. And we can also account for other external forces such as air resistance in the future. Thank you.